Okay, for people joining this live stream, we are talking about logic programming. And the fundamental difference between what we normally do and what is usually called logic programming is what we normally do is you give an input, you go crunch, 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 you get an output. In logic programming, you're given a goal, given a current state and a goal, potentially, and you're asked, how do you get to that goal? What is the relationship between this and things like reinforcement learning and so on in machine learning? Do we know? Do we know if there's a machine learning story around this? So, I mean, the most straightforward case is like find string replace path, where you're given a set of string rules and you're asked, can you go from here to there? Right? Or find the path. Now, you might want one path, you might want multiple paths, right? You might want to know things about the path, but not actually need the path. So to what extent have we designed find string replace path? Do we know all its various arguments and so on? Do we know what, did you understand my question? Do we know what questions you want to ask about find string replace path? And how do they relate also to the things that we do with multi-way system? Because in a sense, find string replace path is a story related to a string multi-way system, yes?
Mm-hmm. So you can get the paths in terms of states, in terms of rules, and in terms of rule application positions. And you can also get the multi-way fragment and the causal graph fragments for the shortest paths.
See this? Can I see this? Where is that documentation? Can I see this somewhere? I remember.
Yeah.
I remember implementing some of that stuff. Can you tell me where it is? Is it in the physics code Dropbox, or is it somewhere else?
I can put it in the physics Dropbox one.
No, but where is it right now? Is it just in your?
Yeah.
Okay. So can you put it there? Okay. And then, so in other words, this is, find string replace path. What we're going to talk about here is, possible results. Things like, is there a path? That's one question you might ask. What are the elements on the path? What are the rules? What are the events on the path, right? Does that make sense?
Yep, it's in my folder in the physics code development.
Okay. Okay. So then we have the question of one path or many. Oh boy, the proof object, right? Okay, comments from people about this and about how this relates to, so this is, there's a question of what's the most efficient algorithm for this, but this is the pure string case, right? The more general case is find replace path.
What is the algorithm for this?
Well, I think an algorithm was some kind of A-star-ish, pathfinding algorithm, but they may be better.
Okay. I mean, remember back in August when I did that comparison against A-star and things, the simple recursive thing that I tried seemed to be the most efficient. But I'm wondering, I'm genuinely curious, what was found to be optimal? Because I haven't followed it since.
Well, you know what? I implemented something also, and then Rowan implemented something which I never got finished.
Sorry.
Yeah, go ahead.
No, this was after. I mean, the original thing that I designed that you then added some syntactic stuff to. I then compared against Rowan stuff and to my own implementation of A star, and it was, I think, quadratically more efficient. But
what does it do? What was it doing?
So it's the obvious divide and conquer approach, right? You just say, you want to get from X to Y. You don't actually have to generate the whole multi-way system that goes from X to Y. You can invert the rules because they're string rules, so they're invertible. So you can generate a forward multi-way system from X and a backwards multi-way system from Y.
Oh, right, I remember this. Yeah.
And then, but then once you found that, once you've put in one pivot, a bit like with a pivot search or something, you can actually put in multiple, and so you can go to arbitrary recursion depth.
How do you deterministically know you've reached the right thing? Because I mean, if you've got two searchlights, but from two different places, you know that they're going to cross somewhere. But if you have a whole chain of searchlights, you might be on the wrong path.
Right. So the only place where it's guaranteed to be more efficient is in the case where you have a single pivot. If you have multiple pivots, then effectively you have to start. You go to the first pivot point, and then you start from there, and you start from the middle. Say if you've got three, okay. And then it may or may not intersect with the pivot point you found. In which case you move to the next pivot point, and so on. So it will eventually reduce to the one pivot case, but in some fraction of cases it will be more efficient.
Okay, so Carlo and others. So what do we know? Carlo has a summary of logic programming languages here.
Yeah, in terms of search, I can tell you that there's basically two main approaches. Prolog uses depth first, which means that if it can get stuck in an infinite chain. Minicanron.
That's exceptionally lame. I mean, relative to what we're talking about, that's an exceptionally lame approach.
Yeah, but Prolog, the difference is that here you have the goal, and in Prolog and in Minicanron you can generate the goal, so you don't have to give S2. So it's like, give me all the possible things for the first 10 that that are true in this.
Okay, so this is so just so I understand that is okay, so it's asking, like the multi-way system, so you're saying it might be something like find string replace select or something, where you're asking for, can you find, i.e., can you find with these rules, can you get to something which satisfies this constraint? Is that right?
Yeah, pretty much. There is a difference in what the rules look like between Prolog and Minicanron, in that the rules of Prolog are horn clauses, and so they are basically implications, and the rules in Minicanron are always two-way. So basically, Minicanron is designed.
We discussed that before, yeah, right? We discussed the fact that, okay, so this is, this is the rule types, right? And the rule types could be, either A arrow B or A left right arrow B, right? Those two cases. And I understand. So you're saying, but so the cases of use, and again, the string case is an impoverished case. The real case is the pattern case.
Wait, on the other hand, I think that in the case of Prolog, it would be better to write it as it's actually A, and then the arrow goes the other way around, and then you can have B, C, D, E, F. It means basically if B, C, D, E, F are true, then A is true. That's usually the way it's written. It's like a reverse.
I see. Okay, so there's a different case here, which is the multi-input rules, which is something we've also encountered in multi-way systems, right, Jonathan? Where, this is like,
I think I brought up last time that there's an analogy to chemical computation and the general problem of lemma formation in how horn clauses are represented in logic languages.
So it's multi-input, multi-way systems. which are basically saying, if I understand correctly, which is also known as branch-like, what will we call them? These are rules that can take branch-like separated things. Am I making sense? Things from different branches of the multi-way system can be combined together in the rule, if I'm not mistaken. Am I making sense? Because you've got all these clauses floating around, and you can combine multiple ones to make the next thing, right? Whereas in a normal multi-way system, there's a single state, and that state is having things act on it. Am I right? Jonathan?
Well, yeah, of course. Yeah.
But wait. You're saying, of course, but other people are not agreeing. So let's clarify. Do you? I mean, actually, I for completely random reasons, I implemented a little multi-way system here. So this is just doing. So in the multi-way system, this is saying, right here. What am I doing here? Multi-way system. What the heck am I asking for here? Oh, I see. All I'm doing here, I'm not allowing, I'm forcing one to have two strings, and I'm then looking at I'm collecting together pairs of strings, right? And then from that, going to the next step, right? Which is, I think, what you're talking about here with the prologue case. Yes.
I mean, the classical example is like you want to define a grandparent clause, and you have the parent clause, and you're saying basically for A to be a grandparent of C, A has to be a parent of B, and B a parent of C.
Okay. Question: how is this related to our SPARQL query language? And is Tony here?
That's an excellent question. So some of the ideas in Datalog, which is a constrained version of Prolog, are related to SPARQL, in that basically they've been included in the SQL 99 standard. It's kind of hierarchical things. So it's called recursive with. And so basically, for example, you wanna imagine you have a database with a bunch of people and their managers, and you wanna know basically who's the CEO, who's the manager of everyone,
right.
something like that. Which was impossible to represent in older versions of SQL.
Okay, but so how is this related? Okay, how is this related to SPARQL? How is what we're talking about? So in other words, the chain of connections, right? SPARQL allows you to, do we have Tony here?
Tony's not here, no.
Could you please try and see if you can find him?
Yeah.
Did you find Roger or not?
No. He has not responded to the request.
Okay. Michael, do you have any comments on the SPARQL relationship here?
No, I'm not enough of an expert. Other than, like, the SPARQL is more kind of, you have little fragments. You don't have so much the big picture in mind.
But in SPARQL, if you look at things like SPARQL property path, it's exactly that. If you put a pattern in the SPARQL property path, basically you can do hierarchical rules and recursive rules.
Right, an RDF triple is a fragment of one of these. It's okay. So, in a sense, what is the relationship? Okay, so relation to SPARQL. The question is,
the relation to SPARQL is actually, there are languages where it's clearer than SPARQL, and there is another version of semantic web that is actually based on Datalog, which is called something like IntelliDB or something like that. But basically, the whole idea of I wanna know whether, you want to compute something that has an arbitrary number of steps in it. That's the relation. It's the
I understand.
The transitive closure of relational algebra, basically.
Okay, I understand. So this is very category theory like also. I mean, it's very like these are morphisms, and we're looking at, well, I don't know, morphisms have a built-in transitive closure idea to them, whereas these do not. But what you're saying is we can imagine fragments, just like, okay, so the generalization of string replace path would be that we have multi-element string rules, right? And that we're basically matching against those. We're saying, is there a path that can be formed from these RDF triples?
But I'm not entirely sure that you can do it with strings, because strings are inherently, strings. So you can't take something from the beginning of the string and something from the end of the string. On the other hand, this kind of rule systems have a set of
I'm aware. I'm making we're using strings one gulp at a time. We're not breaking the strings into pieces in this case. Do you see what I'm saying? So this would be whole string. If it was strings, it's whole object / whole string transformations. Do you get what I'm saying?
Yeah.
Right. So whereas a string, you're expecting to do substrings as opposed to substrings, which I think is different from the SPARQL case. See what I'm saying? In the SPARQL case, you're dealing with these, you're dealing with a whole collection of complete strings which have transformations between them.
Yeah.
Maybe my logic knowledge is impaired. Why is a horn clause based declarative prover any different from a Glocal string multi-way system?
You're dealing with things from, opposite ends of branchial space there. Okay, let's try and unpack that statement. Let's first of all remember what a Glocal multi-way system is.
There are these things that I invented that no one seemed to show any enthusiasm for, which I think are great, but which are string multi-way systems where you effectively shatter the string into each element of the alphabet for the substitution system, and you have so each event operates on branch-like separated characters, but the events themselves have isomorphism testing, which I thought, at least at the time, was equivalent to a declarative horn clause-based prover. That was part of the reason for building it, but
could be. I don't know. I don't know. It could very well be. Okay, so hold on. So the claim is Glocal multi-way systems. Question mark. A world of horn clauses. It sounds plausible. I mean, what implication? So that would be saying that what you'd be doing is, i.e., what we want, i.e., we would need find string replace path in a Glocal multi-way system rather than an ordinary multi-way system. How would you formulate that?
So Stephen, I just sent you a picture of what I mean. I mean, the Glocal multi-way code is not yet WFR'd, but
okay. Wait a minute. You sent it an email, or?
Yes.
Okay.
Question in the meantime. So by you're using the adjective glocal, so it has properties of global and local systems. Is that correct?
Exactly. So it has the property of local multi-way systems that inputs for events can come from branch-like or space-like separated places, but it has the property of global multi-way systems that the events are merged on the basis of some isomorphism testing.
Sorry, say that again, Jonathan. So wait a minute. You've shattered the string here,
right,
into AB.
Right, and so you can see there that the first event is ingesting 1A and 1B, which is why you have two arrows going in, one from the A, one from the B. And it's outputting two A's and a B, which is why you see two arrows coming out and connecting to the A, and one arrow coming out connecting to the B. Right.
Oh, I see. After those, right, I get it. After that, why those are in sequence, I don't really know. Because normally in a multi-way system, there is no sequencing. The fact that this is a BBA sequence is more information than a multi-way system usually just has a bunch of states in it.
So same with, I mean, there's no sequencing here either.
Oh, so then this is just counting the number of A's and B's.
In effect, yes.
Okay, so these are strings in name only. They're commutative strings, effectively. Is that correct?
No, because I mean, you could treat them that way if you only looked at the states, but but the events still have all the structure that you care about. If you get out the causal graph for this, right, and you just look at the event structure, it still has everything that a global the reason I constructed it was precisely because the events encode a global multi-way evolution and the states encode a local multi-way evolution. So the reason it's called a Glocal multi-way system is kind of, as Jan, I guess, pointed out, was that actually all of the information to construct either a global or a local multi-way evolution is contained in this one object.
I don't really understand this object yet. So the order matters. This AB, the order matters. Is that true?
But it matters in the event, because the structure of the event.
I can see it matters in the event. But I mean, these things effectively have additional tagging not visible to us that says that B state is a B7 state that must be in this position type thing.
Right. I mean, you can enforce the property that concatenation is commutative if you want. And actually, I mean, I have examples where I did that, but this is one where it isn't.
Right. Sorry, I just have a bizarre problem here. Just a second. What on earth is this doing? Help. Just a second. Hold on a second. Oh gosh, this is really stupid. Okay, maybe this will work. Who knows? Okay, all right.
Anyway, sorry, my only reason for bringing this up is just that, at least from my understanding, this is formally equivalent. You know, having a rule that says B goes to AB is formally equivalent now to a rule. I mean, that's actually stronger than a horn clause because it's saying B goes to A and B, which is not normally how you define it. But you would split that up into two rules: one saying B goes to A, one saying B goes to B. But the point is, because you can have multiple input characters, that at least that component of the rule structure simulates a horn clause.
Okay, but wait a minute. So I don't yet understand how a local multi-way system with a multi-element string on the left works, because I hadn't realized that this is right. I hadn't realized this just has is, as somebody called it at one point, monogenic. It has a single. It's a neighbor independent setup here.
Right, but actually that doesn't matter. I mean, even if the rule there were AB goes to AB, the edge structure would look the same. It would still have two edges.
How does it know what the order of the AB is? At the level of a state, how does it know the ordering?
That can be. I mean, if it doesn't have a commutativity axiom, then the order is known because the events know the global states.
Okay, fine. But then, yeah, okay. But so then this picture is somewhat misleading because the order in which the states occur here matters.
No, I don't think the picture is misleading. The events show that the order matters, and the states show what happens if the order doesn't matter. That's why the events form a global system, and the states form a local system. If you just viewed the states graph, it would be a local multi-way system where the order didn't matter, because it wouldn't matter whether AB was going in or BA was going in.
Yes.
You just show the events, it's a global multi-way system where it absolutely does matter. And the point is that then the evolution events graph, which is what this is showing, has both pieces. So you can in principle read either multi-way system from this object.
All right, but so the relevance to this is, as we're looking for, this idea of what is logic programming, right? What we're realizing is there are these different cases. There are questions like okay, so another rule type is a multi-input rules, right? That's a case we haven't considered here. This is a case where we say, where you have to have both A together with, when it's some weird symbol here, together with B.
The end.
What's that?
It's usually end. It's it's an implied conjunction.
Yeah, I realize that, right? I don't know. I'm gonna draw it in some decorative way. Okay.
Well, sometimes, often they're just commas, right?
Yeah, in logic programming there are commas. In logic, it's upside down V.
Yeah. Right.
Yeah.
Fine, but I'm just saying these things are present in some bag of things that are present, just like here, the certain states are present, and then events can happen on those states. So this is saying certain events, certain strings are present. It's the same thing in SPARQL. Certain things are present, we can combine them in these ways. Right?
Yeah, and usually A and B can contain blanks that then appear in C, that are captured in C. So
I get it. Right. But the difference between that and find string replace path is find string replace path is going into sub-elements of, see what I'm saying? In sub-elements of A and B to do things. Same with find replace path is taking a series of expressions, a single expression here, and saying, how do I use a rule that can go into the sub expressions? Okay. Does this make sense? So it's the difference between branch-like and tree-like rules, I claim. So find replace path is still doing its quotes tree-like rules, unless it has multi-input, in which case it's branch-like. Does that make sense? Jonathan, does that make sense to you?
Yeah, but again, I'm trying to figure out why is the string replace path, why is the replace path case of this any different from doing the recursive replace path algorithm we described earlier, just with a Glocal multi-way system with wildcard characters?
It might not be. I'm just not there yet. It might not be. Right, and that might be the most general case. But the thing I'm trying to understand first is we've got several different things running around, right? We've got several things we want to do. Like, given the path, and maybe SPARQL is parameterizing some of that as well. What are the elements on the path? Let's look at some of this. Okay, so this is wildcards on a path, right? This is finding a path with wildcards on it. Test whether a query pattern matches. Is there a path? Right? Limit the number of solutions, okay. What is an aggregate? Oh boy. That is a way of doing of multiple paths. I think this is a way of counting. This is a path counting thing.
Well, aggregate is the same thing as the SQL aggregates. So it's things like mean, count, min, max, string join. So
yeah, I get it. But in terms of paths, that's a path counting story, isn't it?
It can be used for that, but it's not just that. You can use it to ask things like, how many generations do I have to go back? And in that case, it's counting path, but you can also ask, how many children do I have? In that case, it's not in the path, it's counting the leaves. Aggregate is really, in general, in relational algebra, is something that takes something that is vector-like and turns it into something that is a scalar. Nothing.
I get it. Right. Another thing that we might be able to do is return tree objects, return graph objects from a find. This is okay. So, we can certainly return graph objects, return graph for a multi-way graph fragment. That's enough.
Do this for find string replace path.
Yeah, right. No, I noticed that. Okay, all right. So this is the SPARQL story here. So let's go back to, and again, I haven't yet understood Jonathan's Glocal stuff, Okay, so that's still on the shelf here. But I'm trying to understand what is the most general kind of question that we're trying to answer. And then how do we break that down into simpler versions? So this case here is not a traditional pattern matching case for us, right? The case SPARQL in principle can be done by our pattern matching, I think. Is that a true statement? We're finding these paths, and it is very much like in the whole physics project. We're simply finding, does there exist? The SPARQL thing is ultimately a hypergraph, is it not?
Yeah, it is. It's it is a hypergraph, and it can be done with the pattern matching in basically with replace repeated or replace list. I mean, it's both really, replace repeated and replace list, because it finds all possible.
Right, but it's also related to Tony's subset replace.
Yeah, sure.
Right, that's another. I mean, this is okay. So there's a relation to.
Yeah, it's related because in general they are unordered. All the clauses are unordered. All the relations are unordered.
Right. So subset cases would be the thing that finds kind of the. I mean, that's how subset cases is built.
Which is the internal implementation of multi-way system, or
right?
The multi model thing. And obviously, in that case, you have commutativity anyway, precisely for this reason, because you have an unordered set. So then, actually, the Glocal multi-way system becomes much more natural.
Which means I have to understand it. Oh well. Okay, but let's go back here. Okay, so let's go back to the logic programming stuff here. Okay, so this is based on horn clauses. All right, so then the basic question that is being answered is, here are a bunch of essentially implication fragments. Can these be knitted together to make a path from here to there? Is that true?
Yeah, or the other case, which you call find string replace select, is what are the things that you can produce with this? Give me the first 10 you can produce, or something like that, that satisfy a constraint, or
okay,
which is basically, well, that idea is used much more powerfully in mini-cannon-like systems, because they can be used to, I mean, if you have a small enough language that you can basically invert, then you can ask it to build quines and other interesting animals.
And mini-cannon can do the mixed case as well, right? Which I think also is not a general feature, where you can specify a partial goal and a partial set of implications, and it will fill in bits.
Yeah, mini-cannon, basically at the end, it has a unification, but also a reification passage. And so it basically can reconstruct new variables that are basically not quantified.
Right.
So they're not unified to anything. So,
but I remember when I was looking into like Alene TAP, which is this declarative theorem prover built on top of mini-cannon, it could do if you give it a theorem, it could find the proof, which is the path counting, but the path finding case. And if you gave it a proof, it could tell you the theorem, which is the checking case, where that's the endpoint case. But it could also you could also specify an incomplete theorem and an incomplete proof, and it would fill in possible details, which is kind of the intermediate case.
Yeah. And you can also basically generate all programs that have a certain characteristic.
Okay, so you could say, one case apparently you're saying is a partial theorem plus partial proof.
Right.
So, what can be filled in?
You specify part of the endpoints and part of the set of the total set of implications, and you ask what are the consistent sets of things that could be.
Right. So this is essentially a cases game. This is some generalized cases. It's asking what, I think. Maybe it isn't. Maybe it's a generalized. some kind of generalized subset cases or something. Not quite sure. Okay, so the more obvious theorem proving case is like find replace path. I.e. find a proof going from A to B. Except that's not. See, that's not the case. That's not the multi-input case, right? That's not the case that we've discussed. Am I making sense? That's not. There's another case which is.
I don't see what the. I don't know. Maybe there's some complexity I'm missing. I don't see what the issue is, right? You've got it. In the language of multi-way systems, you've got a sub-branchial graph to sub-branchial graph input in which you give essentially a collection of paths. That's the theorem proving case, right? You've got the collection of paths. What are the possible branchial graphs that are consistent with those paths? That where the endpoints form sub-branchial graphs that are consistent with those paths. That's the proof checking case, the inverse. And then you've got the case where you specify maybe some paths or partial sections of paths and partial specifications of sub-branchial graphs. And you ask what's consistent with that.
Right. This is all sensible. Okay, here's the unfair part of this situation, right? All this stuff with branchial graphs and multi-way systems and so on, this has all just been invented in the past year, right? So the ability to unify this whole story in terms of those things is kind of you make it sound obvious, but it's in a sense that obviousness is rather recent. Fair?
And it's lost on me totally, for example.
Yeah, well, right, because this is a new way of thinking about these kinds of things, and it's a very nice unified way of thinking about them. And it's one that it's one that gives us the opportunity finally to do logic programming like things in an organized way, because it unifies all these different cases of this and that, and which is what Jonathan is basically saying. Fair, Jonathan?
I think so, but I mean, I don't think the ideas of that. I mean, yeah, the vocabulary for reasoning about them is new, but in a sense, that's what logic programming languages like Minicannon have been doing implicitly.
Oh yeah, implicitly for millions of years, right? The thing is that they haven't seen pictures of actual multi-way systems. They don't have the notion of events. I mean, they do have the notion of events, but they don't talk about them that way. I mean, I just think this is, yes, I mean, this is a sort of a grand unification thing. And it's also, I don't think the world of SPARQL is that close to the world of logic programming usually. It should be, but it isn't.
It's a much smaller subset. It's the data log is the connection. So data log is basically a non-Turing complete version of Prolog that doesn't have basically the expressions are much simpler. You can't have arbitrary nesting in the expression, and basically that's where they got the ideas that led to the transitive closure of SQL. And then
so what is Z3? I mean, I've certainly heard of it for millions of years, but
so Z3 is one of the most powerful of a family of SMT solvers. SMT means satisfiability multiple theory, and so it's like SAT, the Cook one, but with extra stuff, not just Boolean variables, and it's very fast, very powerful. There are links to many languages. I mean.
Okay, so what is it doing? So I mean, right now we have satisfiable Q for Boolean expressions that's quite efficient. It uses a pretty good SAT solver, right? So explain to me what an SMT solver is relative to a Boolean expression SAT solver.
Okay, so Boolean expression SAT solver only knows about Boolean variables, and so all the things that appear. So you have all the variables that appear are implicitly Boolean. In an SMT solver, depending on what theories you put in it, you can teach it about integers, you can teach it about strings, and so on and so forth. And so basically,
okay, but I don't understand. So what? Go ahead. What's the explain to me what is the definition of yeah, I just don't know what
why don't you click on that hyperlink? There's probably that hyperlink explains it better than I can ever, because then it depends a lot on what SMT solver you're dealing with, because different SMT solvers have different theories.
Okay, it says by example here, so. Let me see an example of one of these. So one thing we could do, obviously, is to connect this to what we have. But what is this doing? What is this doing? That looks like algebra, which seems like the very wrong thing to do this with. Anybody know what this is doing? Okay, Carlo, do you know what this is doing?
I don't know exactly that one, but I played a little bit with S3. And I mean, you can use it. It's a bit complicated to explain, because you can use it as a theorem prover, basically, and so you can
exactly why these people have removed the in-out symbols. Okay, so they're using satisfied, but okay, so at least this is, I understand, this is similar to, right.
I mean, as I understand it, these are all just specifications of predicate logic statements, ultimately.
Okay, as opposed to propositional logic for a standard SAT solver.
Right. So if you took a SAT problem and you replaced what would have been, Boolean variables with Boolean elements, and you replace them with predicates that are quantified over some set of non-Boolean variables, then you get an SMT solver.
So you can have some that have lists, some have strings, some have numbers, and you can basically do the same kind of thing you do with a SAT solver over numbers, over strings.
So, okay, but by that,
types as well.
Okay, but so what is the relationship between that? So is this like in multi-way systems, for example, we can have this idea of essentially a reverse multi-way system in which you have a soup of lemmas and you're trying to combine them to get to true. Is that the same kind of thing that you're doing here?
Yeah, I would say yes.
Okay. So again, I'm trying to understand how to. Okay, so what we basically want to achieve is, like, for example, this concept, find replace path, it's a very clean concept, right? Everybody understand this concept, right? It's just, you're given a set of rules and you say, how do you get from here to here? It's very easy to understand that concept. So similarly, I mean, what we're trying to do is we're trying to unify these sort of the many tentacles of logic programming into a small set of concepts like this, where then we can go underneath it and actually potentially have different implementations for different particular things you're trying to get out. Does that make sense? So, and our use case, I mean, honestly, the SPARQL system that we have, other than the few SPARQL endpoints that exist in the world, which it's fun to use, I don't think we've had much use yet for our SPARQL system. That doesn't seem to be a thing that's showing up very much. I mean, we've got our own version of something like that in the surf framework for Wolfram Alpha, but it's not specifically using SPARQL. It's using our own stuff that's optimized in different ways.
I mean, I think one of the problems with SPARQL is that, I mean, there's a very steep learning curve, especially if you want to build your own set of truths out there. So SPARQL you can only use with things that are already existing, more or less. So like, otherwise you have to set up server and start.
Well, I know. I mean, like, for example, we're using Wikidata. You know, we have Wikidata data, which is using that SPARQL endpoint. But the SPARQL queries you can do, I don't think people are mostly doing very sophisticated SPARQL queries against it. Look, the use cases that we've discussed, I mean, the pure path use cases are things like, like game trees, like chemical reactions, like the visualization pipeline, like that would be an example. Can you get to, given this set of data, can you make a histogram out of it?
Yep. And there's stuff like, for example, code simplification and optimization can be done.
How?
So, for example, in Clojure, they have this thing called core logic that does that. Basically, you can tell that two snippets of code are equivalent by feeding it transformations. The problem is,
we've done many experiments with that. They have been rather unsuccessful.
Yeah, I think that one big hurdle for us is that in the case of minicanron, they are effectively, since they start from Scheme, which is a very small language, they basically can write the eval Lisp thing in a way that is reversible, because the whole language can be written in a reversible way. Think about something like append.
No, I understand. Look, we have collected a large number of theorems, code equivalence theorems, right? And I agree that that's I mean, look, simplification is another version of this, where we have the same exact type of thing. And remember also the thing I was talking about a week ago or something, this obstructions framework, where you're doing simplification. So there's another question here, relation to the obstructions framework. Right, so you remember the obstructions framework. The obstructions framework is you are getting to a certain point, and if only you could assume that this was an integer, everything becomes easy, right? But you're not assuming that. So it becomes this very complicated thing. And how do you provide a mechanism where you can easily say there is a path, it just requires this one assumption? Right, Marco on our live stream is commenting that yes, that this SMT idea is basically using data structures to simplify search space and so on. Okay, so look, our main challenge here is to package this stuff in a way that's actually useful, right? And I claim that find replace path is an easy to understand and somewhat useful thing. What do other people think about that? Right, so imagine if you're doing code equivalence. Okay, so you're saying there is a notion. I mean, there's okay, so find, replace path, select bad names might be for things like, e.g., simplification, right? So with simplification, you're given a collection of rules and you're told, yeah, you see, that's more of an optimization problem, right?
Well, it depends on how, if you have a, like in Simplify, you have a kind of a weight system that tells you this is simpler. But otherwise, this stuff can be used to generate sometimes infinitely many equivalent expressions.
No, I understand. But I mean, absolutely, like a multi-way system. I mean, a multi-way system is just you're applying these transformations in all possible ways. You get this whole network. It has many mergers and branches, and we've got a whole theory of mergers and branches, et cetera, et cetera, et cetera. But this is, I mean, let's see, what will be
but I don't know if it should be called find replace path. To me, it's something like replace repeated list, something like that, and then cases if you pattern to it.
No, but I think what it is find replace objective, as in simplify. So look, there are different. I'm going to have to go soon, but there are. This is very interesting. I mean, look, this is a sort of grand unification opportunity. We're not there yet, but right. So this is a case where basically you are given, find, replace, objective might be given. Okay, you've got this rule. You can use apart. You can use together. You can use, I don't know, some other random rule. Blah 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 goes to blah blah blah. Or I can write this as a rule: x blank goes to a part of x, and so on. Right? These are all. Do you see what I'm saying?
Yeah. Yeah, absolutely.
And
And
so
then, but then, what does the objective look like?
I would say the objective could be leaf count. So find, replace. I mean, look, actually, this is more like find, replace, maximize, or minimize, or whatever. Minus leaf count, whatever it is. Find, replace, minimize, whatever. So then this is more like find, replace, objective by leaf count.
Not sure about.
No, find, replace by.
But what's the underlying? So what would be the underlying thing without the objective? So like generate them all.
Yeah, I think so.
Generate 10. What would that be called?
I don't know. But I mean, what this essentially is doing, and this relates very closely to the design of multi-way system, which look, what is the difference between these things and multi-way system? Answer: multi-way system is a big gulp. It's generating the whole thing, the whole graph of all these transformations, right? And we're doing things with that whole graph. Whereas these functions are all dealing with paths through the graph, counting pieces of the graph, and so on. Does that make sense?
Yeah, and I think we should make clear the way this works in terms of whether it's a replace all, replace 0, infinity, or replace the whole thing, level 0. Sorry.
See, I mean, we're planning to actually have multi-way system be a system function. Okay, so much of what we're doing is finding subparts of the multi-way graph, right? So the multi-way graph, it is sort of our new activity, because we think it relates to physics among other things, to kind of look at the whole multi-way graph, as opposed to all these other things where people are like, I'm afraid of the whole multi-way graph. Let me just try and find a path. Does that make sense?
Yeah. Well, one thing that I would like to talk about, if we manage to have another meeting about this, is also pattern unification. So what it means to have a two-way pattern with blanks on both sides.
Yes, I know. That's the thing we need. Actually, this thing that I found, this sat thing by example, is quite useful because it has a lot of Wolfram language stuff in it. And it shows kind of how this seems useful. This seems something that's worth us reading.
Can we have it? Like, can you put it somewhere?
Yeah. Lou is asking, why is there a find before find replace path? Yeah, it's a good question. It probably shouldn't be. I mean, usually we put a find before something to indicate that it is not guaranteed to get the final that there isn't a unique thing that is just find seek, and it's not guaranteed. Like find minimum doesn't guarantee to actually. It will do its best. It will go search for a minimum, but it doesn't necessarily reach it. Let me just.
I think in this case it's more like the difference between replace and replace list. Like,
well, replace list is giving you the spray out at a particular node in the multi-way graph. It's giving you the possible things that can happen. It's not giving you a path through the graph.
I get that. But what I'm saying is that with respect, like the difference with the find functions, like find minimum and so on, is that this guy is possibly finding all of them. You can tell it to halt after finding 10, but it's probably going to return a list unless you have a minimizer version of it.
Yeah, Lou is commenting on the does replace not apply find first. No, because this is a different thing. This is saying you're finding a path rather than doing the individual replacements. Yeah, Marco is saying you're basically finding a path and see all possible computations. That's correct. And Thirsty is commenting, you can't be sure they're global minima other than brute force. Well, sometimes you can. That's what, there are cases in which you can prove the theorem that you've got quotes the minimum. And that's,
these algorithms are all brute force, really. Smart brute force, but brute force.
Well, I understand. One can make certain, and Jonathan is commenting that this is all related to the expressive power of non-deterministic Turing machines. Yes. I mean, this is the story. I mean, in a sense, a multi-way system is a packaging of non-determinism.
Right, but specifically when you were talking about applications, this seems like an obvious one.
You mean everything that's an NP problem?
No, I mean proving theorems about the expressive power of NDTMs, which is otherwise hard to do. If you want to prove, universality of an ordinary deterministic Turing machine, that's just a single origin point, single endpoint find path problem.
Yes.
Right? But in this case where you want an extended, branch-like subgraph to branch-like subgraph, and you're finding a collection of paths, or you want to know if there exists a collection of paths between the two, that's an expressive, that's a statement.
Well, I'm glad you're giving an ad for the thing that I just posted about 3 days ago. Yes, I agree. It's hard. I tried to do this. This is a story of multi-way Turing machines, right? And it's the story of what, when one multi-way Turing machine can represent others and so on, and what possible paths there are that can be found in them. Yes. I mean, this was a kind of a multi-way exploration of that, as opposed to, which I think is the most, are you making a different point?
Yes, a completely different point. So okay. The problem that you, I think, first came to me with, I noticed it didn't make it into the bulletin, but this point that if you construct a Glocal multi-way system for a Turing machine, which I've done, then this question of what is the encoding of a particular state of an NDTM, you can effectively express as a branchially extended tape state, right?
Yes.
Which you otherwise couldn't do in a global multi-way system, which is what my old code, which you're using here, is doing, right?
Well, you're saying that there is a way of representing a collection of NDTM states as a branchially extended object. I agree.
No, a single NDTM state as a.
What do we mean by NDTM state? Do we mean one of the states here, or do we mean a state that is obtained by looking at this whole step?
Well, I mean a state of the NDTM, which is a superposition of classical TM.
Fine. Okay, fine. That's what you mean by a state.
Yeah,
right.
A state of the NDTM.
As opposed to a state of the underlying Turing machine, which has now become non-deterministic.
Right.
Right. Okay. And so then what were you saying?
Well, the point is, if you construct the Glocal analog of that, right? So so each position on the tape is now a single object on a branch-like hypersurface. Then exactly the same problem that Mini-Canron is solving is the problem of determining, can I evolve from a particular NDTM tape state to a different NDTM tape state, which dramatically simplifies the problem of proving, say, universality results of NDTMs. Because it makes it much closer to the classical TM type argument.
You're saying, consider a lump of branchial space and ask, can you get from one lump of, so we have pictures someplace here, of pieces of branchial space. So you're saying, does there exist a path to get from one place? I'm not quite sure what you're saying.
No. So my multi-way Turing machine function, if you generate the branchial graphs from that, which I think is what you're doing here, you get global multi-way states.
Right.
which is very far removed from how you would express the state of a single classical Turing machine.
That's true.
Right. The expression, in order to get it closer, what you want is something analogous to the tape state and the head state of a single classical Turing machine.
That's true.
Which is exactly what you would get if you took each position on the tape and had it occupy a different point in branchial space and had events that operated on those. In other words, if you had a Glocal multi-way representation of this, right?
Say that again. I'm sorry. Say that again. Sorry, I got distracted.
Tape position, and you have it occupy a separate position in branchial space, would just be a separate node in the branchial graph.
Mm-hmm.
Right. Then that's then you have a representation that's much closer to that of an ordinary classical Turing machine. You have a tape, a single head that happens to be branchially extended, but that kind of doesn't matter, right?
What? Wait a minute. The tape is in branchial space or what? I'm confused. I'm completely confused here.
Okay. So the formal definition of what a Glocal multi-way system is, right, is you take whatever the state is, you decompose it into its character set, and you have each element of the character set occupy a different vertex in the branchial graph. And then the rules don't operate on states, they operate on subsets of characters that can be localized or non-localized. That's the fundamental distinction, right?
Localized in, so are you thinking of this Glocal system as being transformations on branchial graphs? Can you think of it that way?
Of course, that's why it relates to the whole mini-canron. That was the point I was making, right? That it's when you say here's a collection of propositions, here's another collection of propositions, you want to get from one to the other. You're finding a collection of paths that map from one subhypergraph to one subgraph of a branchial graph to another subgraph of a branchial graph, with rules that are Horn clauses that act on sub-branchial graphs, which is very different from the global multi-way case, right?
I understand. So the claim is, okay, so first of all, for other people's benefit here, I mean, these branchial graphs are a map of state space that are mapped by common ancestry of state space. So go ahead. What were you going to say? So
right. If you construct the Glocal analog of this, each character, which in our case is going to be a single tape state position, occupies a single vertex, just like in any other Glocal multi-way system, right?
Well, wait a minute. Given a tape configuration, there are two issues in a Turing machine. There's the tape configuration and there's the position of the head.
And the state of the head.
And the state of the head, yes. I mean, I've been considering a lot of one state Turing machines, so that doesn't really matter there.
Right, but in my multi-way Turing machine implementation, the tape state and the head state are effectively treated. They are essentially concatenated and treated as a single kind of thing you can do substitutions on, right?
Yes.
Right. So all I'm saying is apply the procedure I just said, but to the case of Turing machines.
Sorry, which procedure? I mean, so we've got a tape.
You take the character set and you have each element of the character set occupy a single point in the branchial graph. So in that,
each element on the tape at a particular position, which is not what you were doing with the strings, or were you doing that with the strings?
Yeah, that was the.
Okay, but then what you're saying is, for the Turing machine, okay, let's go back to a friendly Turing machine.
That's why with the strings, there were two separate global strings, A, B, and BA, but they occupied 4 points in branchial space.
Okay, fine, but then they were tagged. So in other words, we're saying this particular position on the tape, which is position 13 or something on the tape.
There's no tagging. This is, as I mentioned, that this is just interpreted from the event history. There's no additional information beyond what you already see in the evolution events graph. What you're describing as tagging is just a statement about event ancestry, which is already part of the system.
Okay, but to make me less confused, let's imagine we tagged all of these. So this thing has been shattered into something that says, cell 13 is white. Right? I've got a whole bag of those things. Cell 13 is white, cell 13 is orange, whatever. And then my branchial collection is something which has both, unambiguous cell 13 is white, and ambiguous cell 13 could be white or it could be orange. Is that true? Where I have 2 points.
Yeah, but the point is that in the Glocal setup, you don't make any distinction between that. The whole point of that formalism is you don't make a distinction between separation on the tape and separation in branchial space. There are just separations, and the tagging occurs because of event ancestry, because the events operate globally, just like they do in multi-way systems.
Yes, I understand. I mean, what you're doing is you're knitting the things together by virtue of their event ancestry.
Right. In which case, as I said, the problem of proving expressive power of an NDTM becomes the same as the problem you would solve with a logic programming language, which is certainly not true in the global case.
Well, that's cool. That's cool. Maybe I think that's highly relevant to what we thought we were going to do our physics live stream about. So we've now made a grand unification of I mean, I don't fully understand this yet, but is it your claim? Okay, there's a piece to what we're doing here which has to do with patterns for expressions and things like this.
Right, which is the multi-way operator form of the same thing.
Indeed.
Which again already exists.
What do you mean already exists? You mean you wrote it?
Yeah.
You wrote the multi-way system case of that, right?
Well, there's the multi-way, there's the Glocal multi-way, and the recursive finding case for multi-way operator systems. Yeah.
What did you call them? The recursive finding case?
It's not in the function repository because I thought someone else was taking over the find replace. I thought Mano was taking over the find replace project, but
okay, but you claim it as a part of the find replace path family.
Well, the recursive algorithm I described doesn't care what the system is. It just cares that you have a multi-way structure, right? All it's doing is it's finding intersections between forward and backward.
I get it. Yeah, I get it.
So it does. So because multi-way operator system does pattern unification internally anyway, that code is trivial. I mean, the code to actually do the path finding is trivial.
Okay, but the pattern unification part, that's a separate issue, which is two-way patterns, right? So I mean, this is another thing, is two-way patterns,
right?
Which we don't have right now, right? So two-way pattern is something of the form, f of x blank, g of y blank, two-way arrow, h of x blank, y blank, something or other.
Right. And obviously the way we get around that in both find equational proof and in multi-way operator system is by paramodulating. But we can, undoubtedly, there's a more elegant way of dealing with it.
What is the paramodulation operation again?
So that's where this is the operation in superpositional calculus where you just convert bidirectional equations into unidirectional rules. So in that case, if you have a two-way pattern rule, you can convert it into a pair of single-way pattern rules, where there are only patterns on one side.
I see.
That's what the paramodulation operation allows you to do.
Well, so why don't we have a function called paramodulate?
That's a good question. We probably should.
So which would take a two-way rule like this, and we could imagine, paramodulate that two-way rule, and it would give us a pair of one-way rules. Is that right?
Yes, right.
Is it obvious what that pair of one-way rules would be in this case? I mean, is it?
When there's because you have overlap of the in the case this case it's quite easy because you don't have overlap of the non-variable subterms, so you don't actually have to unify anything.
Right, but if I did that, I would probably have a more complicated story.
Yeah, that would be tricky, and it would be more tricky if you had, say, an operator G on both sides.
I see.
Then that's the case where you'd have to compute MGUs. But without that, you effectively just say, you have X pattern, Y pattern, X pattern equals Y pattern. You just convert that into a X pattern goes to Y literal, and a Y pattern goes to X literal.
So here's an embarrassing admission, okay? In the last third of a century, so the way our pattern assignment system works, right? It will try to put more general patterns after more special patterns, right? So if I say f of x blank equals blah, and then I say f of 1 equals blah, it puts the f of 1 in front of the f of x blank, right? And one of the things that I spent a bunch of time worrying about when we first set that system up. Actually, that system was even built for SMP, but anyway, when I first set that system up, I worried about this question of in what order do you really put patterns in, right? Because in general, two patterns do not have a one is contained in the other relationship. Okay, and so in a perfect world, the right way to do this is with unifiers, I think. That is, given two patterns, what we want to do is we want to say, I mean, the question is, what is the right way? Do you understand the question? That everybody other people can, this is, do you understand the issue here? Anybody understand the issue?
I think I do. So you're asking, it's the problem of ordering down values, basically.
Yes, it's the problem of ordering down values. Right, and what do you do? For example, let me say I have a down value that says f of x blank semicolon prime q of x. And then I say f of x blank, slash Goldbach conjecture, whatever it is, some kind of something. I don't know, this is a bad example, but I mean, some kind of Goldbach something or other thing here, right? What order? That's a bad example, but what order do I put these in? See what I'm saying? One of them is of unknown generality relative to the other one. Right? Is there a consistent ordering? Answer no, which is why we punted on that issue. But in simple cases, we do it. In more complicated cases, we don't. It turns out that is just fine in practice. Because as soon as it gets complicated, you typically don't do that by using the automated pattern rule. But I think that there's this whole question about general unifiers and so on is what you need in order to address this question. For these, Oscar, are there many instances of two-way rules? No, actually, two-way rules are pretty rare. We only introduced the two-way rule construct very recently, and that two-way rule construct is, look, for example, graphs, undirected graphs. It's useful, and oh yeah, here's a really weird example, which is transpose. It's a useful way to represent that. Sorry, go ahead. What were you going to say?
No, I was going to say, but isn't this provably undecidable?
Of course.
Yeah. Okay.
Of course it is.
Because when I wrote the Wolfram language implementation of mini-kernel, I basically decided that the only way, I mean, the main problem is condition. Once you have condition, you kind of have to punt. But if you just have because I mean the condition could actually be effectful and whatnot. So if you're using just straight patterns, you can kind of unify them. You can define a way to unify them.
Right. Well, by the way, what happened to your mini-canon implementation?
Oh, you have it. I sent it
something
to you
we can put in the function repository?
No, we haven't.
But could we? Does it have a smallish number of functions, or is it a big thing with 65 tentacles?
I mean, the point is that for it to actually be useful, I mean, there is a micro version of it, micro Cameron, which can be written in a small, but it's of limited use unless you start writing what they call in the book the bizarre word version of normal function. Otherwise, you can't do much with it.
Okay. Well, all right. Listen, we should wrap this meeting up. Actually, bizarrely, the topic that Jonathan and I were planning to talk about in our physics working session is bizarrely related to all of this. In a just wasn't intended at all. But I think it's very related. Okay, we better wrap for here. Oh, Nick is saying has a function that kind of converts a rule into a two-way rule, replaces all left-bound pattern variables, some careful treatment of pattern tests and conditions. That's interesting. I mean, I think this is it's a problem that we have not run into very much, but it's something clearly for the theorem prover, this is highly relevant. This two-way pattern thing is highly relevant. I mean, Jonathan, if we had properly handled two-way pattern things, what would that do to find equational proof? Could we generalize that in an easy way?
Well, it would mean that we could avoid paramodulation, which would make the code a bit cleaner, but that's really not the bottleneck. I mean, like efficiency-wise.
But in terms of the presentation of a proof, is it relevant?
Somewhat. I mean, it would change. It would mean that we no longer had to. Okay. Here's one obvious way we could perhaps improve the understandability of the proofs. Right. In a proof object, we make a distinction between the construct and the rule. Right, where we say construct, axiom 3, rule, pattern goes to literal or something.
Yes.
Right?
Yes.
If we had a way of handling two-way patterns in a consistent way, we wouldn't have to make that distinction because the construct itself could be a two-way pattern rule. In which case, the patterns and the rule, the constructs and the rules are the same thing. I guess that's something we could change potentially.
Right. I mean, see, one of the things that's really weird here is that the proof objects that we are generating from find equational proof are not that different from the things that we would want to generate. I mean, they're almost like SPARQL sequences, and there are a lot of things that are very similar here. There is a grand unification of all of this that is, that basically the way to think about this, and maybe this is what you're trying to say and I'm not yet understanding it, is, normal computation, like a Turing machine, is, you're following a path. We've got this non-deterministic computation that is, represented by this multi-way graph, and now we're trying to understand things in terms of non-deterministic computation, which is indeed, this has been my last month of kind of how to think about non-deterministic computation. Maybe we should take that up in a few minutes. And fair enough. All right, so we will continue live stream in about 10 minutes on our physics project, and I need to get some lunch, otherwise I'm going to become completely incoherent. So thanks everybody who's been in this meeting, and thank you to folks on the live stream.